Good morning, good afternoon. I'm Peter Denning, welcoming you to the next section of the Artificial Intelligence course, Harnessing Artificial Intelligence. Today's topic is going to be automation. Remember, in our hierarchy of possible AI machines, we said the lowest version of that was automation, and here we're going to be talking about what appears to be classical automation. So we've been talking about automation for hundreds of years, before there was electronic computers, before there was artificial intelligence. So we use that as our baseline. And I think our speaker today is Josh Kroll, and he's going to be looking deeply into the question of what is automation. And I think one of the things he's going to be trying to tell you is that a lot of the things that we see artificial intelligence machines doing are actually higher forms of automation. If I got that wrong, you're going to correct me, right? So let me say a couple of things about this. The urge to automate things with machines goes back a long time in human history. So we have records of Greeks doing simple things like trying to automate clocks. So they have machines that would keep track of the time for you. And then all throughout the ages, you see people trying to make machines to either amplify usually it's to amplify force. So a war machine can hurl ordnance much farther than you can do with your arm. So it's a much more potent weapon that way. And in more recent times, we've started to have machines that can help us do our intellectual tasks faster and better. One of the most common examples of an automated system is the autopilot on an airplane. I think Josh will be talking about that in a few minutes. But a real autopilot has a lot of stuff in it besides computers. Some of them still have gyroscopes in them, I think. But so true automated systems are usually a lot more complicated than the software that's in them. We also know of a famous example of in the 1700s, I think it was around 1770, somebody built a machine called the Mechanical Turk. And it was a machine that played chess. And a lot of people came to see this machine playing chess and were amazed that somebody could build a machine to play chess. Well, it turns out to have been a hoax, because there was a chess player in the cabinet underneath using mirrors and levers to move the pieces and watch what was going on the board. So even though it was a hoax, it still stimulated a lot of interest in the question of whether you could get a machine to actually do that. Could a machine actually play chess and beat a human being? And for many years, even after the beginning of electronic computers, there was a big quest to build machines that would be so good at chess they could beat beat human beings. So that's a quest for automation that's been going on for a long time. So artificial intelligence, of course, goes way beyond trying to play games and tries to do a lot of other things this way. So I'd like to introduce Josh Kroll to tell you about all this stuff with automation. Josh is an assistant professor here in our computer science department. And I think you're here 3 years now.
2 and a bit, yeah.
Yeah, so he's
almost 2.
He's in his 3rd year here. And we actually know Josh from a long time ago. He came here, I think in 2003, as an intern from York High School, and has always been a friend of the department. He went off to get a good education. So he got his undergraduate degree at Harvard and his PhD from Princeton. And then he came back here to be with us. And so we're very pleased to have Josh here with us, studying all these things that he's been studying. So Josh, it's all yours.
All right, thank you, Peter. Peter is alighting the fun we had working on computer science education curricula with a blue ribbon commission that he brought together back when I was in college. So I want to start out today, though, by talking about automation through the lens of the world's most popular restaurant, That, of course, being the restaurant invented or developed in 1940 by the McDonald brothers in San Bernardino. The big invention, the big differentiation of the McDonald's hamburger stand was not the hamburger, not the menu that you could get there. It was what they called the speedy system. And the speedy system was the system by which you could get your food immediately after you ordered it. What made that possible was the use of automation, or what they called a fully automated kitchen. Now, the McDonald's brothers' fully automated kitchen didn't mean that the kitchen was operated entirely by machines. It meant that every piece of food that came out of the kitchen was made in exactly the same way. Every hamburger had the same number of pickles, the same amount of ketchup and mustard. They had built some special gadgets to help them achieve that, but those gadgets were still operated by humans. And that brings me to, I think, a key definition of automation. When we say, what is automation? We really mean that we take tasks done by humans and we situate them within machines, but that is a kind of a byproduct of the core essence of automation, which is that we take a task and we reduce it to a set of established rules. Of course, I'm an engineer, so I want to refer to those rules as a specification, a way of describing the behavior that the machine should have. And that specification defines what the machine should do exactly precisely, and whether that specification is operated by humans, as in the case of the McDonald's kitchen, or by machines, we enable automation. We enable the operation of the process in an automated way. And you see automation done by humans and machines, and even humans and machines working together. And so we'll talk later about humans and machines working together and how there aren't really any situations which are fully automated, which means that in every situation there is at least a human deciding what should the rules be, when should the rules apply, when should something real happen in the world based on the rules saying something. And so we want to talk a little bit today, as Peter was saying, about what it means to automate something. I'm going to start that discussion with another example. This example is from around 1800. This is a picture of something called Meyer-Day's automaton. And there were a number of automata that were developed in the 1700s and early 1800s, devices which appeared to do something that would have previously required a human. In this case, Meyer-Day's automaton draws a picture. And the way that it draws a picture is it has a number of articulated joints, and the movements of those joints are controlled by these sort of notched gears. And as the gears turn, the automaton can move its articulated joints, and the end result is a picture that looks something like a picture a human would look. And that provides us with a machine that does something that we would think was a human-only task prior to this. Another example of automata from the same, or not automata, another example of automation from the same period of time is the Jacquard loom. So the Jacquard loom is a device which used a set of punched cards to determine which threads in cloth should be shown during a weave and which should be hidden in such a way that when the cloth was produced, it would at the end produce a pattern. And that pattern used to be set by master weavers, by humans who would go around and adjust the settings on the loom to make the pattern. With the advent of these machines where the pattern could be set automatically, the price of these high-end cloths plummeted, but as a result, the idea of wearing patterned cloth became sort of widely available to the public and remains so today. And just to kind of put a point on that, this is a picture of an operator taking a pattern drawn on a piece of paper with squares on it and converting the pattern in each square to a punch in the card. These cards can then be laced together and fed into the machine and control the operation of the machine that way. And it was in fact this mechanism that inspired Charles Babbage, who designed one of the first machines that was meant to automate numerical computation, to his design, which also used punched cards. And some of you may be familiar with the idea that punched cards were important in the development of electronic computers. Peter said that I would talk about the autopilot, which I will now. This on the right here, on your left, is a picture of one of the original Sperry autopilots. Lawrence Sperry developed this technology as contract research for the US Navy in about 1912. 1913, he demonstrated it to the Navy. In 1914, famously demonstrated it at an air show in Paris, where he got out of the pilot's seat of a plane, walked out to the edge of a wing, and hung off the edge of the wing to demonstrate that the plane would continue to fly without a human at the controls. Of course, today's autopilots are much more capable, much more complicated than the Sperry autopilot. So instead of just maintaining altitude and heading, modern autopilots can integrate with things like GPS navigation and allow pilots to set waypoints and entire flight plans before they take off. This allows pilots to operate planes in a much more automated fashion and refocus their work onto more strategic work like navigating around weather or navigating around air traffic, keeping the schedule organized. A final example of automation, I said it can be implemented with machines and also with humans. In fact, originally the word computer referred not to a machine, but to someone on a team of humans working together on a mathematical computation. That computation was done by individuals on this team and then cross-checked by other individuals. People would work on different pieces of it, and then each person working together on their little calculation would lead to the entire computation being done by the team and being checked by the team. And those teams were referred to as computers. And it was only later that the electronic machines that replaced these teams were referred to also as computers because they performed the same function. In this case, this is a team of computers working at Bletchley Park on code-breaking activities during World War II. And I think all of these examples show something important about automation, which is not so much that, as Peter said, that automation is that artificial intelligence is a higher form of automation, but rather that automation is moving to more and more tasks that we used to think of as requiring input and operation by humans. So today we have machines, software machines, which can detect and identify and classify objects in images, stills, and videos, which can transcribe speech to text, and which can do other things which up until recently we thought were too complicated for humans even to write programs to do because we couldn't figure out how to write those programs. This has led to a call that there is lots of capacity to build artificial intelligence machines that are as capable as, say, a human brain. And that, I think, is a long way off. And one reason I think that is because whatever we think of as intelligence is a little bit slippery. And what we've done when we say that is we've kind of restructured the problem. We've moved it from the problem of identifying what is artificial intelligence to the question of identifying what is intelligence. Now, intelligence can happen in lots of ways. So if you think of ants, we don't think of ants as being individually very intelligent, and yet they build these quite large, quite complicated structures. Here on your right is a casting of an anthill in plaster. But anthills aren't just complicated in shape, which you might attribute to them being built over time or being added onto. They're complicated in function. So anthills tend to have the right amount of airflow to keep the colony at the right temperature so that the ants can survive, so that the ants can breed, in some cases so that the ants can grow food. Many species of ants grow fungi, almost farmed, inside their anthills that they can consume. And this behavior is not the result of the ants thinking through carefully how do we get the anthill to exactly the right temperature. It's based on the ants responding in simple ways to simple stimuli. In other words, following rules. Those rules are then tuned over time by an evolutionary process. And that idea of rules that get kind of fine-tuned repeatedly to optimize some objective, in this case the survival and reproduction of the ants, that's very similar to the way a lot of artificial intelligence technologies that we have work. To that end, I wanted to spend a moment talking about search engines and whether we should consider search engines to be artificial intelligence. So here I've asked a search engine yesterday a fairly simple question: who is the Secretary of the Navy? And the answer, when I asked, was that Thomas W. Harker, is the acting Secretary of the Navy. How does that answer come to exist? Well, I want to show you this diagram. This diagram is from a paper that I believe is titled "The Architecture of a Large Hypertextual Web Search Engine." That paper was written by two computer science grad students up the road from here at Stanford University. Their names were Sergey Brin and Lawrence Page. Some of you may recognize them as the grad students who dropped out of that program to start a little company called Google. This diagram is quite complicated, but actually we can sort of group the components into a few more simple classes of component. And what we can see is that the search engine is basically going across the internet and making a copy of it with the crawler, storing that copy in a database, and then analyzing the documents that it has found and analyzing the queries that we give it, and using a ranking model to match the analyzed documents with the analyzed queries to figure out which documents to return to our query in the best possible way. And by doing this very well, it seems like the search engine is smart enough to answer our questions. It seems like it's artificially intelligent, but in fact, each component of it is just acting in a simple way according to rules, just like the ants. Again, prefigured by Peter's introduction, this brings me to the idea that intelligence, as we see it in machines, can be embodied in different ways, not just through complexity, but sometimes through the inclusion of the teaming of humans with the machines. So on the right here, or on the left here, you see the automaton that could play chess, or so people were told. In fact, someone was inside the cabinet underneath the automaton, looking at the state of the board and controlling the articulated joints of the automaton from inside the cabinet using a series of levers. This was called the Mechanical Turk. It was from 1769. Peter was very close. For those of you who don't believe that you can play a game of chess well upside down on the roof of the place you're in, I recommend to you very highly a particular Netflix series that you can go find. On the right here, you see a still from the classic 1939 MGM movie based on the 1900 L. Frank Baum novel about the gold standard, The Wizard of Oz, which shows a different kind of system in which a machine is teamed with a human. In this case, the great and powerful Wizard of Oz is nothing more than a carnival barker acting as the proverbial man behind the curtain. And so sometimes people refer to these systems as Mechanical Turks, sometimes they refer to them as Wizard of Oz systems, but they very much are systems that we see in the real world. So for example, until recently it was not known, it was not disclosed to customers that the Ring doorbell, which seems like a device that can analyze video and tell you if something interesting is happening in front of your door, was operating purely with software-based automation until some reporters figured out that actually the software-based automation was really just recommending to some workers in a work center in Poland that the video footage might be interesting. And then it was up to the workers to decide whether or not that level of interest was sufficient to justify notifying the user that, that the video constituted something interesting the user might want to look at. And that brings me to another kind of automation from teaming that I think is a good analogy, which is that automation changes the way that we do work by the nature of what parts of the teaming humans are good at and what parts of the teaming machines are good at. So these are robots from Amazon warehouses, and they can find shelves in the warehouse which have products on them, and then they have a little sort of a screw on top of them that they can raise to engage into the shelf, lock the shelf into place, and carry it across the warehouse. And when they get there, a human has the job of removing the item from the shelf and putting it in a bin so that it can be packaged and shipped out. And it's very easy for a robot to find a shelf, to position itself with respect to the shelf, and to lift the shelf. Robots are good at that. They're strong. This problem is very well specified. It's easy to figure out, where in the warehouse is the particular shelf that I need to get. Where am I with respect to the shelf? But robots are not so good at picking up objects from a shelf because the objects might be different sizes. Some of them might be slippery. Humans are very good at. We have these things called hands that we haven't yet developed machines that are quite as good at solving this task. And also, it's not clear where on the shelf the object will be, and that's also a difficult problem to solve. Once the object is picked and packed, then the package itself is much more normalized, and it can be sorted by a different kind of machine, a package sorter. And the package sorter sorts packages, but in a way that's very different than the way humans might sort packages. So you can use this machine to, for example, spread out packages using a conveyor belt across the warehouse so that you have packages going out, different carriers in different loading docks, different trucks in different loading docks going to different locations. You can sort the packages out based on that to make loading the trucks very efficient. That's very similar to another kind of automation that we can talk about, which is the automation of cargo shipping and logistics more broadly, which previously was a job that required many thousands or globally millions of longshoremen and stevedores who did the work of gathering cargo out of warehouses, bringing it physically into the holds of ships, lashing it down, balancing the ship, and so forth. And we're doing the opposite, taking the cargo out of the ship and bringing it into the warehouse. This required the warehouses to be very close onto the docks where the ships were located. Today, of course, we do this in a very different way. We have unbundled the problem of packing the boxes into which our goods go from the problem of moving those boxes around. And once the boxes are standardized, we can use the same cranes, the same trucks, the same train cars the world over to move these boxes around because we have a standard that allows us to define how long the boxes are, where they need to be grabbed in order to be lifted safely without damaging the cargo, and we can stack them onto ships by the thousands and make cargo shipping much cheaper. And that work, by the way, was also done as research for the US Navy, in this case to simplify and make more efficient the operation of logistics during the Vietnam War. And if you happen to drive up Highway 880 to Highway 580, going up toward Berkeley, Sacramento area, you will pass the Port of Oakland, and you can still see the original 3 Sealand cranes out at the end of one of the quays of the Port of Oakland, sitting there from the Sealand company that had that original contract to develop this technology for the Navy. Another way in which automation shifts the concept of work is that it changes the work that's left over for humans and changes the nature of the way we interact with systems. So, for example, if we were to automate the work of a conductor, it wouldn't maybe make sense to have a bipedal robot that walked down the aisle of a train. That might be quite dangerous. The robot would fall on people. Robots tend to be heavy. People don't like to be fallen on. Human conductors tend to be pretty good at not falling on trains after some time. Instead, we invent fare gates. Fare gates are very efficient. They're very easy to turn into an automated system, but they have the downside that if you have a system based on fare gates, you cannot go with your family, with your traveling companions, all the way up until they get on the train unless you also have a ticket. You have to pay to get into the fare gate zone. Whereas if you go on a traditional sort of train where the tickets are checked by a conductor on the train, you can hang out with people who are traveling right up until they get on the traveling vehicle. And that's kind of a trade-off in the way that we feel the system works. Right, one is very sort of separating the people who are in from the people who are out by a gate. The other is a little bit more accommodating and maybe pro-social. Similarly, you see that kind of reframing in other places. So in hotels and airports, you see check-in operations being automated through the use of kiosks. In hotels, you see work done by humans turned into room service deliveries by robots. What's interesting there is that people tend not to tip robots for the deliveries, even though there is a similar amount of human work being done maybe to get those items to you. That work is just hidden from you. And then below you see a kind of showpiece robot which calls itself the Maker Shaker, which makes cocktails using 2 robot arms. And of course, another way to think of that is that we've had the vending of drinks automatically for a long period of time. So we've had vending machines for decades now. We've had vending machines not just for drinks, which can be pre-mixed and pre-packaged, but for food, even hot food, which can't. This is a picture of a restaurant automat from something called the Horn and Haddart Company. The Horn and Haddart Company lives on as a brand name, but no longer as an operator of restaurants. Although I think recently someone did open a Horn and Haddart branded restaurant in the East Coast somewhere. And you might think, well, there aren't really automat restaurants anymore, and up until 2019, mid-2019, you could have gone in many major cities to branches of this company, Itza, which was operating an automat-style restaurant. But what's being automated is not the full operation of the restaurant, but the collection of payment from customers and the serving of food. So you would order on a little kiosk tablet, and then your food would be placed in a box by a human, and your number would come up, and then the box would unlock and you could get your food. And that gets me to a kind of final notion, I think based on the amount of time I have, which is that automation acts not on jobs that people have, but on tasks that people do. So when we think about a restaurant worker, they do a bunch of things. They prepare food, they clean up after the customers, they collect payment, they serve the food, they find out what the customers want and act as wait staff. And some of that work is easily automated, some of that work is not easily automated, and so what we end up with is a restaurant that looks similar to a restaurant that we're familiar with, but also somewhat different. And people will often say that things like the advent of autonomous vehicles will eliminate jobs like taxi driver or truck driver. But actually there's a lot involved in those jobs beyond operating a vehicle. And so while it might be the case, and there are reasons to suspect that it isn't the case, which I'll talk about in just a second, that we would be able to automate those parts of the job, there are other parts of the job like in the case of a truck driver, dealing with the accountability for the cargo, or managing navigation in a strategic way given the weather and given construction, given traffic, that might be somewhat more challenging, although navigation has become something that has been more successfully automated recently. But the takeaway message is that the narrative about jobs being replaced by machines tends to be a little bit problematic. So I've called it a myth here. That's a bit of a strong claim. That's on purpose. I would say that it's certainly the case that automation in the shipping industry, the switch to containerized shipping, did lead to the loss of many thousands of jobs, but there are still lots of people engaged in the container shipping business and in the logistics industry. It's just that those jobs have moved around and the nature of them has changed. And through some policy choices that have been made around those developments, some people have been advantaged by those changes and other people have been disadvantaged by those changes. And so I want to talk briefly at the end here about the difference between rules, which I've said automation is operating a process with regard to, or according to a set of rules, and other ways we might organize a process. So rules are very simple. They require no interpretation. Once we specify the state of the world and what the rule is, we know what the outcome is. That means we can apply the rule in an objective way. We don't have to guess what the rule means. It doesn't mean the rule itself is objective. The rule could be incredibly discriminatory. But the rule applies and it gives us the outcome. And that gives us something that, as computer scientists, we call scale. It means we can apply the rule really fast to a really large number of cases. And that means that we don't have to worry about how the rule applies, because it's just that's the rule, and we apply it. If you talk to philosophers of law or legal theorists, they will tell you that there are other ways to organize requirements on a process or in a policy, and those other mechanisms can be more expressive and more flexible, and maybe better in some cases. Sort of the next level of that hierarchy up is what's called a standard. So standards are something like the rules, not the rules, but the organizing, the way that we think about whether or not the copying of, so if you write something or take a picture, you have taken an act of creation and you have fixed it in a tangible medium, right? Either you've written your words on a piece of paper or in a Word document or something like that, or you have taken a photo digitally on film, you've fixed it in a tangible medium. Under United States law, that means that you now own the copyright in that object, in that photograph, in that writing, whatever it is. Whether you go to the Copyright Office or not doesn't matter, you own that copyright. And if I copy your photograph by, say, putting it in my slide deck, that may or may not infringe on your copyrights. Whether it does or not is based on a standard, a legal standard called fair use. Some copying is acceptable under the law, and some copying is not acceptable. And the standard by which you sort out acceptable copying from unacceptable copying is called fair use, and it's a standard. It requires a decision maker to apply, and the way that it works is it has a mandatory, what in copyright law they call the four-factor test. So there are 4 factors of fair use that define how you apply this standard, and decision maker, a judge usually, would have to figure out how do these 4 factors apply in the particular case. And the factors are things like the purpose of the copying, the extent of the copying. There are 2 others. But standards provide some flexibility, because we don't have to say exactly this kind of copying, or if you copy 35% of an image, that's okay. If you copy 36% of an image, that's no good anymore. There are some rules of thumb that people use to say, well, when the standard is applied, it really kind of gets operationalized this way normally. And then finally, the most abstract sort of way to organize a policy is through principles. Principles are like standards in that they require a decision maker to operationalize, but they're unlike standards in that they don't give you that mandatory list of things to consider. They don't give you a framework to apply. There's no 4-factor test for a principle. So a legal principle might be something like, no one should profit from their own misdeeds. Now, courts do depart from these standards or these principles from time to time. There are cases, there's a famous case in the case of that particular principle where someone murdered someone they were due to inherit some money from. And the court found that they shouldn't actually inherit the money because they would then be profiting from their misdeeds. There was a little bit more to that case, because the way I described it, it sounds like the principle was applied. But there can be exceptions. But there's no kind of 4-factor. There's no framework that applies in a principle. You have to the decision maker has to figure out how to operationalize it. And so I'll close by talking about how we might think about whether rules are appropriate through the lens of automating a very specific thing, which is a speed camera. So here's a speed camera, and it measures your speed and then sends you a ticket by looking at your license plate number if you are going too fast. Now, a human police officer can figure out if you're driving over the speed limit but safely or under the speed limit but unsafely. The speed camera probably has a little bit of a hard time with both of those things. And you might ask, given the way the speed camera works, where should I set the threshold between infraction and no infraction? Should it be right at the speed limit? For practical reasons, probably not. It should probably be a little bit higher. But how much higher? Well, that's a question that you could try to figure out how to tune. And then you have other problems, like here on the right you see a sign from Germany which shows a very complicated speed limit, one which depends on whether you're driving a car, a truck, or a tank. and one which also depends on whether or not there's any oncoming traffic at the moment. And so actually building out the rules to automate enforcement in the context of these more complex scenarios can be quite a challenge. I'm out of time, but I do want to just flip through one last key point. I'm just going to advance directly to that slide, which is to say that automation can fail in ways that are different than humans would fail in the same task. Just as it reorganizes work that humans do, it fails in ways that reorganize what humans do. And so working kind of from the bottom to the top, some of you may recognize, because there was a big stand down about it, the photograph of the USS John S. McCain, which suddenly and abruptly turned athwart a chemical tanker and was struck. 10 sailors were killed. The reason for that is probably that the bridge team became confused about whether they had handled the contact correctly. They thought they'd handled the contact correctly, but it turns out that they had put the ship into a turn, and by the time they realized the ship was in a turn, they were unable to figure out how to correct the turn in time to avoid the collision. In a similar way, on the left side here, you see the tail section being recovered from a plane that crashed into the Atlantic Ocean, Air France Flight 447, on a routine transit from Rio de Janeiro to Paris overnight. Hit some bad weather around the equator, and its airspeed sensor froze over. When the airspeed sensor froze over, control of the plane was dropped away from the autopilot and given back to the pilots. The pilots were very experienced. However, they were very experienced flying planes on autopilot. They were not very experienced flying planes not on autopilot. What this meant was that the pilots, given a stall warning, acted as though they could power out of the stall by pulling back on the stick and powering up the throttle as high as it could go. But in fact, the other thing the plane had done besides take control away from the autopilot and give it to the human pilots was to move the plane's control system from what was called primary flight law to what was called alternate flight law. In alternate flight law, the angle of attack of the plane is not limited. So the pilots thought, oh, we can power out of the stall, but in alternate flight law, you can't power out of the stall. They attempted to power out of the stall for 6 minutes before pancaking into the Atlantic, and it was a long time into that 6-minute period before anyone suggested doing what would seem like basic airmanship, which is nosing down, getting out of the stall, and then recovering the situation. Finally, more and more you see accidents with so-called self-driving cars, like this Tesla that crashed at the intersection of Highway 85 and Highway 101 up in Mountain View, right by the exit where you get off from Moffett Field, killing at least one of the occupants. The problem in these accidents is, again, a sort of handoff problem between the humans and the machines, where the machine doesn't quite know what to do in a situation, so it quickly hands control back to the human, who isn't paying attention because they haven't been watching the road, because they've been watching Netflix on their iPad, because in some of these accidents they're not even sitting in the driver's seat. So that leads us to a situation where there are big trade-offs between automating something and not automating it. As I mentioned, speed and scale is one of those trade-offs, one of those benefits of automation. Other benefits, automation, by virtue of being rule-based, is very consistent, very reliable, very predictable. We can figure out what an automated system is going to do in a particular situation. We can guess ahead of time, given this situation, the system is going to respond in this way. Automation removes some foibles of humans, like tedium that humans might have doing a job. And they provide some structure to the process. At the same time, little failures in the rules can propagate across thousands or even millions of cases very quickly. When we try to establish a model of the world in the rule set that we're building out as a machine, we might create a situation where we don't represent the world accurately, and that little gap can blow up across many cases and create big problems, and we see that quite often in automated systems. I talked a little bit about de-skilling of humans and the ways in which automation sort of leads people either to a state of passive vigilance, where, you know, if I tell you you have to watch a video feed for a month, and one time in that month something interesting is going to happen and you must push a button exactly when it happens, you're going to probably miss it. So, you know, if we can use automation to reframe that problem a little bit, so that it does a good job of sort of guessing when the interesting thing is happening and maybe sets off a bell for you. That might help. And a final risk is the idea that automation causes the loss of human autonomy or dignity. I think we've all had the experience of calling customer service and getting a phone tree, press 7 to connect to a different menu where you have to go 3 more menus deep before you can actually get your problem solved. So on balance, I tend to be more of an optimist, that what we gain from automation is more than what we lose, but we have to take those risks and identify them and control them. And if that seems interesting to you, I'm actually teaching a course on trustworthy and responsible artificial intelligence next spring in the CS department. So you can look for that. It will be CS 4340. And I'll close by noting this chart by former NASA engineer and current comics author Randall Munroe, who has made a chart of how often you do a task, how much time you shave off of that task. Over 5 years, how much time can you spend automating that task? So if you just look at the top left cell, if you do a task 50 times a day and automating it would save you 1 second per each time, then over 5 years, it's worth spending up to 1 day automating that task. If you can automate it in less than 1 day, then you've saved time over 5 years. Now, it might not be you doing the task 50 times a day in an organization with 2 to 3 million employees, hypothetically. Tasks might happen quite often, and the returns to automation might be enormous. Of course, knowing that and doing that calculation may not necessarily tell you what is and isn't efficient. And so I think I've used already more time than Peter will allow me, and so if there are 1 or 2 questions, I'm happy to take them. Otherwise, we can close out here. Thank you very much.